All right, let's talk about current. Let's do a problem or so here. So, for a circuit to flow, for electricity to flow, right? Usually when we say electricity flows, what we really need to be talking about is current, right? So we already talked about potential, voltage. So the two main parts of electricity, if you think of electricity having parts or ways to describe it, we have a voltage to describe the potential energy kind of thing versus the current, which is the flow of electrons. And so let's say we have an LED. What's an LED? A light emitting diode that needs 20 microamps to light for the light to come on. Say we're connected to two AA batteries in series. All right, so what does this look like in a circuit? It says draw the circuit as first part, so let's do that. So battery symbol is something like this. Long bar, short bar, right? We could put two pairs or we could just have one pair, one long bar, one short bar. But each of these is a AA battery, right? What is the voltage? What potential does AA battery have? 1.5 volts each. So the long bar is a plus, the long bar end is a plus end, because remember potential voltage, potential difference always has to have two sides, right? Where from where to where? What's the low level to the high level, right? So we have two batteries like this, two AA batteries. By the way, AAA have the same voltage, C's, D's, same voltage, right? They can just put out more current, right? And so these are in series, and we can like pretend like this is a flashlight or something. And so we might have a switch that can open and close, right? So the switch closes down here, or it's open to make the light go off. And then we'll have an LED. So we could draw it like this. So we have little LEDs, little lights and things. They're different kinds of LEDs. And the circuit symbol for an LED is something like this, right? And so if it's a light, so there are diodes that don't give off light. They would just be this without the little arrows, and the little arrows kind of tell you that it's a light emitting diode. Okay. And just for reference, this kind of looks like an arrow, and that tells the direction that current flows in the diode. So if we close the switch goes closed, switch goes closed like this, then we can get a current to flow. Right? So a current flowing means charges are moving, right? And remember the definition of a charge moving, or the definition of current is how much charge passes a certain cross-sectional area, or we can think how much charge passes a little, if we draw a line here, like think of cutting the wire, or having a thing where we can see how much current is passing here, thinking of water going through a river, how many gallons per minute go by, same kind of thing, how many charges per second go by, right? How many coulombs per second, not charges, but coulombs per second go by, right? So we could have our circuit looking something like this. When the switch is closed, we get a current to flow. If the switch is open, current doesn't jump across the gap, right? There's an air gap. Current won't go, charges won't jump across, and so then there's no electricity flow, no current flowing. We have voltage still, have potential energy, right? But they're not jumping off the cliff. They can't jump off the cliff or go down the hill until the switch is closed. Then the charges can go down the hill. We have a current flowing. All right, so how much charge passes through each second? So this is assuming that we have 20 microamps and the light is on, and then, so my problem maybe isn't fully described here, but assuming the light is on now, so we have the current. Remember, current is in amperes, amps. So the current is 20 microamps, so 20 times 10 to the negative 6 amps, right? And it's asking how much charge passes by each second. So remember, the definition for current is how much charge, or the change in charge, or over the change in time. All right, or we could just say usually we just assume how much start with 0 and how much has gone past after a certain time. So we're just watching the charge go by, counting how many coulombs go by for a certain amount of time. So we can also just say it as Q over T. Is kind of assuming the initial Q is 0 and the initial time is 0. We could do something like that. I guess we can just keep writing it as delta Q over delta T. All right, so how much charge? So it's asking us for delta Q. Rearranging this, delta Q is going to be I times delta T. So the current times how much time we're looking at. So it says each second. So how much time goes by, or how much charge goes by, how many coulombs of charge goes by each second? We just have 20 times 10 to the negative 6 amps, which an amp is a coulomb per second, right? And so then we're going to multiply that by the time, and it says each second, so 1 second. And so if we remember amps is coulombs per second, the seconds will cancel out and we'll end up with coulombs, right? So delta Q, or Q, how much charge is delta Q, is just, that was too easy, 20 times 10 to the negative 6 coulombs now. Okay. I should have said how much goes by each hour. Let's change that to be each hour. I think that's how I had it written originally when I wrote the problem, but then I screwed up. Okay, let's say we wanted to go how much charge passes by each hour, because 1 second is boring, right? So let's fix this. So now delta T is not 1 second, but it's 1 hour. But standard unit for time is seconds, so 1 hour. So delta T equals 1 hour, which is 60 seconds. Is it 60 seconds? No. Is 60 minutes. Let's go ahead and do it formally. All right, delta T is 1 hour. 1 hour is 60 minutes. Right? 1 minute is 60 seconds. So the minutes cancel, the hours cancel. So 1 hour is 60 times 60. So it's 60 times 60, right? 3,600. 3,600 seconds. There we go. And so now our delta T is 3,600 seconds. Again, seconds cancel with seconds. We end up with coulombs, but let's do that. 20e negative 6 times 3,600. 7.2 or 72 times 10 to the negative 3. So delta Q equals 72 times 10 to the negative 3 coulombs passing through that LED each hour. Again, it's a coulomb is a huge thing. So the LED can light up for an hour and not even get 1 coulomb passed through it. Okay, how many electrons is that? All right, well, this is kind of back to the beginning. So 1 electron is 1.602 times 10 to the negative 19 coulombs. And so remember we have the equation Q equals NE. So E equals Q over, no, we want N. Solve that for N. N equals Q over E. All right, so N equals Q, or delta Q, basically it's the same thing in this problem. 72 times 10 to the negative 3 coulombs divided by the charge for 1 coulomb, 0.602, 1 electron, sorry, and negative 19 coulombs. So we have that number there, so divide it, oops, let's do it. 72 E negative 3 divided by 1.602 E negative 19. Okay, so we have 449 times 10 to the 15th electrons passing by each hour. All right, a lot of little electrons. And draw the direction of electron flow. So the current's going that way, but current is talking about the direction positive charges would go. Which direction would the electrons go? Opposite. So electrons would flow that way. All right. And the electrons, most of the time, if we're talking about copper wire or what have you, are what's actually flowing. So the things that are moving are actually going backwards. But because of the way current and Benjamin Franklin and others defined things at the beginning, positive charges go this way, and so we just have to keep that in our head. Most of the time we'll just think of it as positive charge moving, even though we know in reality that it's a negative. Okay. Part D. If the wire is copper with a radius of 10 to the negative 4th meters, what is the drift velocity? So the drift velocity, remember, is the average velocity of the electrons moving in the wire. That away, I guess. And so we just have the formula for drift velocity in terms of current. Current is we need N, the number of electrons per unit volume. Electrons per volume. Let me get the equation sheet just to give you practice again. Find it so that you can. So we have this on our handy dandy equation sheet. Oh, I actually have it solved in terms of drift velocity. And so here's our current equation, change in average current, change in charge, or the amount of charge passing by for a certain amount of time. Drift velocity is the current over, I was going to write it the other way, current is drift velocity times NQA. And so I'll just continue as I was doing here. So N times Q times A times drift velocity is the current. Yes. So on the equation sheet, the I kind of looks like a 1, but make sure you get it as an I. It's the current, okay? So this is an I. Okay. So, but actually we wanted to solve like the equation sheet has it. So this is the and so this is drift velocity in general. This Q is the charge of the thing that's moving. In this case, it's the electrons moving. So this is actually going to be E, the charge of an electron, and I guess negative E technically. And A is the cross-sectional area that the current flows through, and V is the drift velocity. So let's go ahead and rearrange this like it was on the equation sheet. So drift velocity is the current divided by, and we'll just put E in there, A. Okay, and so we need to know N. So this N, electrons per unit volume, is a property of the material. So we need to get that. So N for copper. Let me just search that up real quick. Free electrons per volume, not the total number of electrons per volume. Well, Google says, we'll see, we'll use what Google says. Google says 8.5 times 10 to the 28th. Electrons, we'll say E minus is as electrons per cubic meter. Okay? And so we've got the current from above, we've got our N for copper, we've got the charge of an electron. What's the area? This is the area. So if, we've got the wire. Anyway, we've got a wire that very large, magnified, and we said the radius was 10 to the negative 4 meters. And so the cross-sectional area is just the electrons are flowing through the wire. So that's just pi r squared, the area of the circle that is the face of the wire end. All right. So A is pi times this r squared, 10 to the negative 4 squared. Okay, running out of room. So let's say our drift velocity then is our current, 20 microamps, 20 times 10 to the negative 6 amps, divided by N, 8.5 times 10 to the 28th, electrons per cubic meter, and then our charge is 1.602 10 to the negative 19 coulombs for the charge of one electron, because that's the thing that's moving. And then the area is pi 10 to the negative 4 squared. Okay, let's put all that in. 20e negative 6 divided by, let's put in some parentheses. First one, 8.5e 28 times 1.602 e negative 19 times pi times 1e negative 4 squared. Okay, so we get a drift velocity of, so when we put it in, we get a drift velocity of 47 times 10 to the negative 9 meters per second. If I did everything right, let's just double check. Got stuff in there good. I think so. All right, which is not very fast. 10 to the negative 9, so one very, very small meters per second, less than 1/1000th of a meter per second, right? But electricity flows at the speed of light, right? It gets there just like that. So how can this be happening? We'll get down. I'm jumping to F. So why does the light seem to come on immediately? You flick a switch and it's just there, right? We can't even see how fast it is or see the delay or notice the delay because it happens so fast. But we can think of it this way. We can think of the wires, right? They have all these electrons in here, and we have electrons here and electrons here. Think of it as like marbles in a tube. A whole bunch of marbles in a pipe kind of thing, right? And so when we flick the switch, that's the same as connecting the pipe to something else that's going to have a flow, and basically we push a marble here. So, but this is full of marbles, so if we push here, one pops out here instantaneously, or if we push one extra one in, another one pops out there just like that, right? It's a they're all connected, and so everywhere, even down very long wires in a power system or what have you, it is basically at the speed of light. So it happens instantaneously to us in terms of our noticing, even though individual electrons aren't moving that fast, bump, 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 but their average velocity isn't that fast, but the electricity or the effect of the flow happens immediately to us, right, at the speed of light. Okay, part E. If we double the charge flowing by, so we're sitting here, we watch, we see how many we had, we had 72 millicoulombs. Now we're going to have 144 millicoulombs go by, right? What happens to the current? Well, Q equals 2Q. Q becomes 2Q. I is basically Q over T, so it's going to be 2Q over T, so I doubles as well. Similarly, what happens to VD? So VD, again, is proportional to I, which is proportional to Q, so VD doubles as well. Okay, let's go ahead and stop there.